Hello, welcome to Lab 2. In this lab we will observe an object falling from rest, analyze it with tracker, construct two computer models based on physics, compare the models to the observation, and answer the what if and what does it mean questions. For my observation, I chose to use the metal lid from a glass jar. I used the diameter of the lid, which was 10 centimeters, to calibrate the measurements in tracker. I set the positive y direction to point upward and tracked the motion of the lid from the moment I released it until just before it hit the floor. Here is the graph of the position of the lid over time. I measured the mass of the lid, which was 0.03 kilograms. Since the object was dropped from rest, its initial velocity was 0 meters per second in all directions. The initial position of the lid was the origin of my chosen coordinate system, and the duration of the observation was 6 seconds. To construct my computational models, I used the following physics principles: Newton's second law and the position update formula. To calculate the weight force, I used the force is equal to mass times acceleration form of Newton's second law, where the acceleration is the magnitude of the gravitational field near Earth's surface times the negative y unit vector. To calculate the drag force, I used the turbulent drag model provided in the lab assignment. Note that b, the proportionality constant for the magnitude of the drag force, is a constant with units of kilograms per meter. For the purpose of these models, we will assume that only the weight force and the drag force exert a significant force on our system. We will also assume that the magnitude of the gravitational field near Earth's surface, little g, is equal to 9.8 meters per second squared. As you can see in this first computer model, I have set the mass of the system to that of the lid in my observation. The initial position is the origin. The initial velocity is 0. The clock starts at 0 as well. The time step, delta t, is set to 1/100th of a second. The magnitude of the gravitational field near the Earth's surface, little g, has been set to 9.8 meters per second squared, based on my earlier assumption. J hat, the positive y unit vector, has been set to point upward. Since this first model will not account for drag, I set b, the proportionality constant for the magnitude of the drag force, to 0. The model is set to run for 0.6 seconds. Here you can see in Python language the weight force formula and the turbulent drag model that I showed on the previous slide. Here you can see the net force is equal to the weight force plus the drag force, which is one of my assumptions while making this model. Here is a velocity update form of Newton's second law, and here is the position update formula. Here you can see a model of the motion of this system, with the yellow arrow representing the weight force vector. Here is a graph of the system's displacement over time. In this second model, we will account for the effective drag on our system. In order to do this, the only changes we must make from our first model is to assign an appropriate value to the constant b. Through trial and error and comparison with my observation, I found an appropriate value for b of 0.0069 kilograms per meter. Here is a model of the motion of this system, with the yellow arrow representing the weight force vector, and the blue arrow representing the drag force vector. Here is the graph of this system's displacement over time. Here is a graph of the position over time for the model without drag, the model with drag, and the experiment. As you can see, the model with drag matches the experiment almost perfectly, but the model without drag overpredicts the position of the lid due to the fact that in the experiment there was a non-negligible drag force. We will now answer the first key question: which models, if any, predict a terminal velocity? In our model with drag, we observed that as the velocity increased, the drag force increased. This points to the fact that, given sufficient time, the drag force will eventually be equal to the weight force, therefore canceling it out, and our system will reach terminal velocity. This is not the case, however, in our model without drag. Therefore, That model does not predict terminal velocity. We will now cover the what-if question. If the object was initially thrown downward, would it reach the same terminal velocity as if it had been dropped from rest? To determine the system's terminal velocity, I took the model with drag and set it to run until the net force was approximately equal to 0, and had it graph the ball's velocity as a function of time. I then reran the same model, only this time I set the initial velocity to be equal to -10 in the y direction to simulate the throw. Once again, I plotted the velocity as a function of time. Here is a graph comparing the velocity versus time for the two models, and, as you can see, they both have the same terminal velocity. This concludes Lab 2.